saw in our previous video that basic definition of the vector operator here is Navier symbol as this vector of partial derivatives with respect to x, y, and z. So now let's take a look at some of the most common operations that we define through that symbol. The first one, one of the most common ones, is what we call the gradient. So when we defined the Navier symbol, we sort of already encountered the gradient, although we didn't call it as such. But the gradient is when we essentially do scalar multiplication. So actually each of these are going to be defined through the different vector products that we looked at in the first video sequence. So the gradient of some scalar phi is equal to d phi by dx times I plus, there are going to be three of these terms, d by dy, d by dz, multiplied by j and k. So that's what we call the gradient. So to understand what is the meaning of the gradient, sort of the physical or mathematical geometric interpretation of the gradient, we can go back to our total differential definition. So if we remember that, if we write dr as the magnitude of the dx vector, so dx was that small distance we were moving from one point to another, so if we define dr as the magnitude of that change in distance, and divide both sides of the total differential expression by that, so the total differential was the gradient of phi dotted with this dx vector. So we have dx, dy, dz. I'll put in my I, j, and k here. So if I divide both sides of that expression by this scalar dr and multiply that into this right-hand vector, so dr, now we can start to make some sense of what is the gradient, because we see that this one, since we defined dr as the magnitude of this dx vector, this one now becomes a unit vector. It just gives only the direction of dx. So this one is equal to gradient of phi dotted with, now I'll say dx hat. So this one here is a unit vector. So now if we think back to how we define the dot product geometrically, we have this dx unit vector, and then if we have this other vector, which is the gradient of phi, it's telling us something about how phi is changing in each of the coordinate directions. So the d phi by dr is equal to the dot product of these. So now if I project the gradient down onto this direction dx, so d phi by dr is this dot product, and that's equal to the magnitude of the gradient phi times the magnitude of dx, in this case is dr, cosine of theta, where theta is the angle between those two vectors. So looking at that, we can see actually that this magnitude here, d phi by dr, is going to be maximized when those two vectors are pointing in the same direction. In other words, since I should actually say this is dx, magnitude of dx hat. And we know that this one here is equal to 1 because we define dx hat as a unit vector. So d phi by dr, the magnitude of the derivative of phi in the direction dx, is equal to the gradient times the cosine of the angle between the gradient and the direction dx. That's going to be maximized when cos theta is equal to 1, right? Cos theta only varies between -1 and 1, so when the magnitude of cos theta is equal to 1, that's when we're at a maximum. And cos theta is equal to 1 or -1 when theta is equal to 0 or 180 degrees. So in other words, when the gradient of phi points in the same direction as dx, then the magnitude of d phi by dr is maximized. So to summarize all of that, the gradient of phi, sometimes you see that written as grad of phi. Some texts use that symbol. And I can say that the gradient gives the magnitude and direction of maximum change in phi. Underline magnitude and direction here. So the gradient gives us the magnitude and direction in which phi is changing the fastest. So to sort of have a physical image of what that actually looks like, you can picture yourself walking up a hill, or you're taking a hike, you're out in the mountains, and you're walking up a trail. So when you look up the hill, the gradient is the direction of steepest descent. Usually we don't hike up that way, it's too difficult, but the fastest way to the top of the mountain is to follow the gradient, actually, at all points, always taking the steepest path up the entire slope. So that's how we can understand what is meant by the gradient. It's the direction of fastest change, for example, of elevation. In our next video, we'll take a look at how we got this through scalar multiplication, and now we'll look at how the other types of vector products can be combined with this vector operator to give us different operations.